Okay. Okay, so now we're on to the second topic, a little bit later than I expected. We're going to talk about reliability and security and do a deep dive into this. And I think this is really important. There's going to be a lot more interesting reliability and security issues that in memory that's going to affect the entire systems. Okay, yeah, this is one of the 3 key challenges that we're going to talk about. And that's an example. Does anybody know who this is? I've given you the name, actually.
It's Maslow's triangle.
That's right, yes. He's known for the triangle. This is Abraham Maslow. He is a very famous American psychologist who dedicated his life basically to understand this question basically. Why do human things do the things they do, essentially? He came up with this hierarchy of needs, and he's well known for this thing over here. Basically, he says that you have to have your physiological needs and safety needs satisfied before you can talk about or think about love. And then before, you need to have that satisfied before you can think about esteem, and you need to have that satisfied before you can think about highest level forms of art and self-actualization. You can summarize this as, who cares about modern art if you're being threatened at the moment, right? And about to die. So that's why we need to start with reliability and security. But if you're really interested in psychology, you should take a look at his work. And his work is influenced by a lot of existential philosophers in the past. There's a lot of interesting stuff. And at that time, like while he was developing his theories, there were 2 major other movements, like behavioral psychology by B.F. Skinner. That was one of the major things. And psychoanalysis, of course, from Sigmund Freud. That was the first one that was developed. And he created one of the 3rd movements in psychology, if you will, together with other existential psychologists. But anyway, he clearly figured out what was the basic thing, and this is true for computers also. I give a lot of these analogies between computers and humans, but this is another example. Does anybody know what this bridge is? Yes?
Tacoma Bridge.
Tacoma Bridge, Tacoma Narrows. Are you from Seattle? No, okay. How do you know this?
Well, it collapsed. So
it collapsed, okay. So people know that it collapsed. That's good. So I get the answer, Golden Gate Bridge. Golden Gate Bridge was actually designed before this, and people who worked at the Golden Gate Bridge worked at the Tacoma Narrows Bridge. This is on the Hood River Canal, a little bit south of Seattle. I crossed the new incarnation of this bridge many, many times to go to the Olympic National Park, and you can do that, but not this bridge. So what happened to this bridge is this happened. Basically, this is a very famous bridge where it collapsed because of aerostatic flutter. There were a lot of interesting stories about it, and if you want to read about the stories, you should really look at this link over here from Washington Department of Transportation. They have a history of the events as to what happened in the collapse of this bridge. But this is an example of a reliability problem affecting security and safety. And actually people were on this bridge, and the professor actually who was doing stuff to understand why this bridge is doing those things, he believed until the very end that the bridge will not collapse. But the bridge collapsed, and he tried to rescue the dog in the car that was on the bridge, but he was not able to, as far as I understand. Okay, why am I telling you this? Because it's an example of a reliability problem that actually affects security and safety of humans. And this is another example. These people who were constructing stuff during the wartime in Manhattan, they look very happy, right? But you can ask the question, how secure and safe are they, right? So if there's a reliability problem here, we may not see these people anymore. So security, in my opinion, is about preventing unforeseen consequences. This is a very broad definition of security. And how do you design systems that can prevent unforeseen consequences? Actually, some of these you can argue are foreseen, but maybe the consequences of the foreseen may be unforeseen, right? Okay, so that's why we need to talk about security. And DRAM scaling problem is is very much about the connection between reliability and security. In fact, this may be one of the very, very critical examples, maybe the most prominent example where we're going to tie a reliability issue in hardware with a huge security problem in the systems. I don't know of any other example that actually makes this connection as strongly so far. We've discussed this already. You need this DRAM circuit to work reliably, and for that to be reliable, the capacitor and the access transistor and the sensing circuitry must be reliable. And we're having issues with the reliability. So this is one example. This is a study that we did with Facebook. My student Justin went to Facebook and he did an internship there, and he analyzed all of the data that they have in their servers worldwide. And they have a lot of servers. Now, don't ask what they're doing with your data on their servers, but they have a lot of memory errors on their servers also. So basically, they have so many servers that they don't allow us to publish the number of servers and the amount of memory that we've tested. But believe me, it's a lot. And this is a correlational study. Basically, you see that as the chip density is growing, the relative failure rate of the servers because of memory errors is also growing. The reason is chips that are larger have cells that are closer to each other, they're crammed, and they're more vulnerable to faults. And this is a trend. Other people have looked at this trend also in Google's and Microsoft servers, and they've seen similar results. Our data is maybe a little bit more comprehensive and newer. This was from 2015. And if you're really interested in other trends that are similar to this, you can take a look at it. But these sort of large-scale studies are very informative because they tell you the trend of what's happening in terms of reliability in this case. And then we also were very interested in exploring this at the small scale. So we built these memory controllers that are essentially FPGA-based memory controllers. Well, yeah, there's a fan over FPGA here, but this is the earliest incarnation of the system that we have. We have these Xilinx boards where we have a memory controller, and we plug this memory controller to test memory chips. And the reason we built it was to study the retention behavior of DRAM, because retention behavior, we knew that that was critical for memory. When we wrote the Radar paper, we said, oh, you could actually get rid of a lot of refreshes, but let's see if we can really get rid of all those refreshes in real life. That's why we had to study this behavior. And while we were doing that, we actually studied many, many other things that I'm going to talk about. And this is one of the systems where we could do many, many parallel memory testing. This is not the newest system, but this is where Rowhammer was discovered, which I'm going to talk about. And we actually open sourced this infrastructure. If you're really interested in doing FPGA-based studies of DRAM, you can download it. This is the paper that we published. It's flexible. We actually have a C++ API, so it's actually a C++ programmable memory testing infrastructure. You don't need to deal with the individual DRAM commands. You just need to use the C++ functions that we provide to actually test memory. And it's open source. You can download it. You can let me know how it goes. You just need an FPGA. We don't provide the FPGA. But it's not, hopefully, that expensive. Okay, so one of the things that we wanted to test when we built this infrastructure was this data retention. I've already shown you this one. Basically, we said, oh, what does the DRAM retention time profile look like? And we figured out it looks like this. And now you can develop many, many mechanisms if you know this information reliably. But we also figured out this is dependent on the location, this depends on the stored value pattern, this depends on time. And we're going to talk about that later. But one of the things we discovered, one of my students, Yungu Kim, and other students working together, they discovered that you can also predictably induce memory errors in most DRAM chips. Now this is a bit scary because of this predictably part. We knew that you could induce errors, right, by changing the refresh rate, for example, or by taking a flashlight or a heat source, putting it next to DRAM, you're going to induce a lot of errors. But we're going to induce errors programmatically, basically, by programming, and predictably. This should not happen, right? And because it's predictable, it causes a security problem that I'm going to talk about as well. This is the DRAM Rowhammer phenomenon, and it's essentially a simple hardware failure mechanism. You may see other people calling it a bug. I don't like calling it a bug. It's really a failure mechanism because it's a fundamental failure mechanism. It can create a widespread system security vulnerability. And later, people started writing articles like this. This is a Wired article by Andy that talks about forget software, now hackers are exploiting physics. And this is actually a really good title that captures the problem, because we're going to exploit physics to take over a system. So what's the problem? Let's talk about the fundamental low-level problem. If you look at DRAM or any type of memory, it consists of basically rows. We've discussed this as a bank structure, right? If you want to access a row, you need to activate the row, apply high voltage to that word line. Now, if you want to access another row, you deactivate or pre-charge that array, apply low voltage. This is just a read process, right? Activate, pre-charge. And if you keep doing this over and over, fast enough times, before the cells get refreshed, it turns out in most modern DRAM chips, adjacent rows get corrupt. Some bits in the adjacent rows get corrupt. They flip, basically. They flip from 0 to 1 or 1 to 0. They basically lose charge. This is essentially the problem. By reading a row repeatedly, many, many times before the cells get refreshed, you can corrupt cells in adjacent rows. Now, those adjacent rows may be mapped to the operating system, maybe mapped to some other application, maybe mapped to your own application, but it shouldn't happen. By reading memory, you should not corrupt memory. Even by writing memory, you should not corrupt memory, right? You should not corrupt memory at all. So we call this the hammered row. We call this the victim rows. And we showed that you can actually induce these errors in most real DRAM chips you can buy today. What does most mean? Most means more than 80% of the chips that we've tested in about 2012 timeframe. The paper is published in 2014 because the first time it was rejected when we submitted. They said that they don't think this is going to be a big problem in future DRAM. So don't give up. And actually, this is going to be an even bigger problem in future DRAM, as we can see. So don't give up if you get reviewer comments like that. Take the best out of the reviewer comments, and some of them you can leave out. Okay, so basically 80% of the DRAM chips are affected for companies who should remain anonymous in this case, but you can guess who they are. There are only 3 major manufacturers. But it's a scaling problem. It's not a company-specific problem. It's really a memory scaling problem. I'll talk about why. So why does this happen? Basically, cells are the rows are too close to each other. As a result, when you activate one row, because of electrical interference, you're slightly activating the adjacent word line also. If you slightly activate the adjacent word line, some vulnerable cells are leaking a little bit. And if you do it enough times, you leak enough charge from the vulnerable cells before the cells get refreshed. And that's why this is happening. This is one of the reasons, actually. There are multiple reasons. It's really a combination of effects that's getting much worse as you scale the size of the circuit down. So the fundamental problem is, as you scale the size of the circuit down, things are too close to each other. There's not enough electrical isolation between the cells. As a result, what you do to one cell is affecting the other cells. In this case, it's what you do to one row is affecting the other rows. And it's a scaling problem because the chips that we've tested that were manufactured before 2010 were not vulnerable to this problem. The first vulnerability we discovered was in 2010, and all of the chips that we tested that were manufactured between 2012 and 2013 actually have this problem, regardless of the manufacturer, and the error rates are very similar. This is error rate on the y-axis and when the chip was manufactured on the x-axis. And the chips are still somewhat vulnerable. We're going to talk about some of the solutions later on. So that was our FPGA-based infrastructure. Quickly.
So what are the reasons that before 2012 wasn't?
Because things are far away from each other. Yeah. The cells are far away from each other. There's not enough electrical interference for this. And this is actually a scaling problem. This affects flash memory. One of the reasons we started looking into this problem because we had the FPGA-based infrastructure for flash memory, and we knew that read disturbance errors were a big problem in flash memory. So we said, oh, why not look at some of these error types in DRAM also, because DRAM was scaling very fast into smaller technology nodes. We're going to talk about flash memory if we have time. Let's see. So this was in our FPGA infrastructure. You could design a memory controller that does this. But the next question is, can you actually write programs that induce these errors? And this is the program that we wrote with that paper. It's very simple, as you can see. What it does is it selects addresses X and Y such that they map to different rows in the same bank. And it ensures that you avoid the cache, you avoid the row buffer, and you basically ping-pong activates to X and Y like this. Not this slowly, but very fast, such that you do it enough times before the cells get refreshed. And if you do it enough times, now my computer is faster than me again. And if the chip is vulnerable, you can get errors. Okay, so at the time we tested, we showed that you could do it on Intel memory controllers and AMD memory controllers. This program, when this program runs, it induces a lot of errors. And errors are correlated with how fast you can access memory. So if you have a good enough memory controller that can access memory fast enough, you can induce these errors. There's nothing special about Intel and AMD. Other people have demonstrated you could do this as an ARM, IBM. It's a very industry-wide problem. You just need to have a good enough memory controller that can access memory fast enough. So it's a reliability issue. It's more of a security issue, actually. And when we first wrote the paper, the first sentence that the paper starts with is, memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. I still believe this. This is really fundamental. You should not have these kind of errors in memory. And we said in the paper that you could actually design an attack that could take over a system. You could compromise a system completely. And the good folks at Google wrote a blog post that basically did that, essentially. This is the Project Zero team, who is very famous for developing these attacks on hardware. They recently also discovered the Meltdown and Spectre attacks, but before they also worked on Rowhammer. And they basically said you could exploit the Rowhammer bug. Again, they don't call it a failure mechanism. Bug sounds more fancy, I guess, and sexy, but I think failure mechanism is nicer because it's a really fundamental failure mechanism that affects all types of memory. We'll talk about that later. They show that you can gain kernel privileges by running a user-level program. So this is directly copy-pasted from Google's blog post, which I would very much recommend that you read if you're interested in system security, hardware security. This is really a blog post to read, and they also have a black hat presentation delivered by Mark Seaborn that you can watch. They basically said they learned about the problem from our paper, and they basically said they explored that in their laptops, and they found about 50% are vulnerable to the problem. And they actually built several working privilege escalation exploits, 2 of them, to exploit this. One of them is not very interesting. It takes over the Google native client. That's okay. But the other is really interesting. It uses these Rowhammer-induced bit flips to gain kernel privileges by running a program at the user level. So what the program does, very quickly, I'll give you the key idea. If you want to really understand the security engineering details, you should definitely read this blog post. They basically were able to hammer memory and induce bit flips in the page table entries of the program that points to the page table of the same program. Now, if you can flip the right bits in your page table entry that points to your own page table, you can flip the write enable bit, let's say. Now you gain write enable access to your own page table, and you can do anything you want to your memory. Right? That's the idea. Of course, it's a little bit more complicated than that, because if you target a single bit out of 64 bytes, let's say, the probability of this attack being successful is very difficult. It's a probabilistic attack, but you can increase the probability of the attack by being more intelligent. So they sprayed the memory with page tables, and they did a lot of interesting stuff. But this is the early work that built on the Rowhammer work to gain kernel privileges. And then people start drawing pictures like this. Is this the end of memory? We're going to talk more, look at similar pictures like this. But I think my favorite analogy, I always like things that are explained in a very crisp manner. I found this on Twitter. Basically, somebody said it's like breaking into an apartment by repeatedly slamming the neighbor's door until the vibrations, perturbations that you cause magically open the door that you were after. Right? So if this place was locked, now you know how to escape it. You keep banging on the walls and the vibrations magically open the door. Right? Well, good luck. I'm not sure if the same failure mechanism occurs in this particular building, right? Okay, so I'm going to go, this is for your benefit, you can take a look at it. This is really the literature that I've collected on attacks based on Rowhammer, and there's more to come. I'm not going to cover this, I'm going to give you some pictures later on, but all of these are actually in your slides. So people have built a lot of attacks. I don't know why my USB is so slow, so we need to figure out USB latencies, of course. So okay, this is one of the attacks over here. These folks from TU Graz in Austria, they basically built an attack where they could induce these bit flips remotely through the JavaScript in a remote server. So they said this, we gain unrestricted access to systems of website visitors. This is very interesting. You can read the paper as to how you do that. This is another interesting attack, one of my favorites. Basically, this is folks from Vrije University in Amsterdam. They basically tested that you could do this in an Android phone. Using ARM processors, and you know the operating system very well in the Android phone. And the operating system has predictable memory allocation patterns. What they did was they fooled, by doing memory allocations carefully in a user level program, they fooled the operating system to allocate a page table for that program in a location that they knew was vulnerable to Rowhammer. And over time, you can figure out slowly whether a location is vulnerable to Rowhammer. Once you fool the operating system to allocate your own page table to that location, you can hammer it and you can gain access. Basically, you take over the system, right? And you can fool someone to download an app that potentially does this, right? Okay, and these are more recent. This is actually May 3rd over here. People have looked at using the GPUs to actually induce these attacks. And whenever you run a program that uses the WebGL interface, you could actually get compromised. And these folks also looked at inducing these Rowhammer attacks through the RDMA, remote DMA engine, on a remote machine again. And this is concurrent work again. This is also very recent. I think this is May 18th or so. Yeah, May 10th. Okay, there are more security implications. This could be another security implication. If your computer is not safe, maybe this is one approach to keep it safe, right? I wouldn't recommend it. So we should talk about solutions. So one of the solutions will be intelligent memory controllers. So in the paper, we covered a lot of potential solutions. You should read the paper for more detail. There are a lot of issues, like make better DRAM chips, good luck. As you scale memory technology, you will run into these fundamental problems, and you'll run into even more problems. So this comes with a cost. You can make it reliable, but you need to isolate things, and that comes at a very high cost. So that goes directly against technology scaling. You don't want to do that necessarily if you're scaling in other dimensions. Refresh frequently. This may not be a good idea. We're trying to eliminate refresh, right? Sophisticated ECC, error correcting codes. People are moving into error correction codes, but there are better solutions than error correction codes, because error correction codes are very good at correcting random errors. If you don't know whether an error will happen, put error correction codes and they will correct those relatively well. But this is a very specific type of error. You could be more intelligent about correcting this. An access counter is basically, can you keep count of accesses to a given row and stop accesses? How do you do that? The complexity of this may be high. Okay, so this was a naive solution is throttle access to the same row, limit the access interval. This is not good for performance. Refresh more frequently. Our actually paper shows that if you want to get rid of every single error in the system, in every single chip that we've seen, you've got to increase the refresh rate by 7x. That's probably not a good idea, because we want to get rid of refresh, not increase the refresh at all. Okay, so this is a solution that's employed by industry in existing, because in the field you have a problem, right? In the field you have all these vulnerable chips. How do you fix the problem? Refreshing frequently is the solution, actually. And I like putting Apple's patch over here. They basically said this issue was mitigated by increasing the memory refresh rates. They didn't say solved, they mitigate the problem. I believe they increased the refresh rate by 2x, maybe 4x under certain conditions. So they basically refresh the entire memory, even though this problem may be localized to a particular location. So this is not a good solution for that reason also. And other vendors release similar patches, and this is, I think, the reasonable solution to employ in the field. But if you had a patchable memory controller, you could program it a little bit more, you could have come up with a much better solution perhaps, right? So what is the better solution? This was our solution, and I still think this is a very good solution actually, because it's stateless. The idea is probabilistic. Basically, after you close a row, probabilistically refresh the adjacent neighbors with very low probability, maybe 5 out of 1,000 times, or 1 out of 1,000 times, or if you want really, really high reliability, 10 out of 1,000 times, right? This reliability guarantee with this number is much better than the reliability guarantee that you get from hard disks. And you only refresh the adjacent rows of the row that you're closing, only once in a while. And you don't even need to keep track of anything in this case, because you know which row you're closing, and you just need to know what are the adjacent rows, and you need to flip a coin. And you can vary the strength, as I said. So we tested it. You can read the paper. The slowdown and the power overhead is very low. It's low cost and low complexity. Why isn't it employed in existing systems? Because the memory controller is not intelligent enough. The memory controller is a fixed entity. If we had a little bit more programmability, we could employ something like this. So how is it going to happen in the future? So if you want to implement this in the DRAM chip, you could actually do this. Existing manufacturers are actually doing some of this. There is enough slack and timing parameters, which we're going to talk about in the last topic. We have plenty of slack. The latencies are specified for the worst case operation, so the margins are very high. So actually, after you close a row, you have enough time. The memory controller doesn't issue a command for a long time because the latencies are specified that way. You could actually sneak in a refresh to the adjacent rows. And that's what's happening in existing DRAM chips. I'm not sure if this is a very reliable solution, because we want to eliminate the slack as much as possible to reduce latencies. So we're going to talk about that. But this is one solution that the manufacturers are employing today in existing DRAM chips that are going forward. I believe a better solution is really doing this in the memory controller. Memory controller needs to know which rows are adjacent to each other in DRAM. This information is not exposed to the memory controller today. Internally, DRAM takes a row address and scrambles it a little bit. Most of the addresses are linear, but there's remapping of the rows that happen because of other reliability issues. For example, after a DRAM manufacturer tests DRAM and figures out, oh, there's a fault in this row, they don't want to throw out the chip, because that's very costly, that affects their yield. So they have some spare rows, and they remap internally this row address to that other spare row. And that information doesn't get exposed to the memory controller, so the memory controller doesn't know exactly which rows are adjacent to each other physically in the memory chip. So that information needs to be exposed, which means that you need a better interface. We've been talking about better interfaces at the beginning of the lecture. We're going to talk about that at the end of the lecture. And you need an intelligent memory controller. So this is another need for the intelligent memory controller. So if you're interested in this, you can take a look at this paper. And I recently written a paper which we're going to talk about a little bit more on the row hammer problem and other problems that we may face going forward. So as I said, industry is writing papers about it too. They didn't talk about row hammer. Row hammer was published at the same time this paper was published, actually. I mean, they were informed about row hammer from us, so we actually collaborated with them quite a bit. Actually, if you see the row hammer paper, there are Intel authors over there. But there are other issues as well, and there needs to be solutions. So intelligent memory controller is a good solution to the problem. And we actually know how to design some of these intelligent memory controllers. This is actually our infrastructure that I alluded to earlier. This is our FPGA-based infrastructure where we can actually test memory chips. We built essentially a flash memory controller and the flash translation layer to understand the reliability and scalability issues with flash memory chips. Flash memory, if you look at it, flash memory has scaled down much faster than DRAM. As a result, it's seen a lot more issues. So whenever flash memory was introduced, it had a lot of errors to begin with. So you had to actually have an intelligent memory controller to correct for those errors. And we actually looked at a lot of issues, and this inspired us to look into issues like row hammer in DRAM. So it's good to always build infrastructure and understand the problems really well, because that could actually enable you to do other infrastructures and discover other problems. And that's why we were able to write this paper. And this discusses a lot of the research that we've done that's kind of summarized over here on the flash memory over here. So basically, the key takeaway is I think main memory needs intelligent controllers. We're going to talk a lot more about that. But I think we'll start tomorrow with understanding row hammer a little bit, since I think I'm exactly on time because I started 3 minutes late. Any burning questions before we part up? Yes?
So what was the average number of times you have to read the row before that is?
So excellent. That's an excellent question. What is the number of times you need to hammer the row, activate the row, and pre-charge before you actually induce the errors? So when we started testing, it was about 150 times, 150,000 times within a refresh interval. But that got reduced. The smart folks at Google, what they introduced was a double-sided row hammer. So instead of doing row hammer in a single row, you actually sandwich the row, and you do double-sided row hammer in adjacent rows, and they reduced it a lot. And later, people have also optimized it. You can do it right now. It depends on the chip, of course, but you could do row hammer within 40,000 accesses within a refresh interval, 40,000 or so.
Yeah.
Okay, one more.
You talk about using machine learning techniques for...
Speak up.
You talk about machine learning techniques for the data controller policies and things like that.
Yeah.
But that was like before the paper, that was about 7 years before. Are you aware of any new research working in this direction using machine learning for architecture exploration?
Well, I mentioned this Google paper, right, that Parth also mentioned. Certainly, I think prefetching could benefit a lot from machine learning, but I think this is a very ripe area to explore. It's wide open. Even in memory controllers, there's a lot more work to do. Yes, one more. I cannot hear you.
Is it possible to change the frequency of hammering to decide which bits you want to change in the adjacent row?
To change the frequency of hammering,
Yes,
you said?
to decide which bits you want to call up.
Yeah, so I think which bits are vulnerable is a function of the hardware. So it doesn't change with the frequency of access, really. Yes?
Was there any real accident caused by row hammer reported accident?
I see. Really? Well, I don't know, first of all. But all I can tell you is there's anecdotal evidence that I've seen where this actually may not be a security problem, but also a reliability problem as well. So there are some applications that actually bypass caches because they keep some of the locks in part of memory. And if you're multi-threaded, you could be hammering that location a lot. And as a result, you may actually get the wrong value. So that's all I can tell you in terms of a real application being affected. I believe real applications are being affected by this, but it's very hard to tell also. So security issues, who knows, right? It's very hard to tell whether a security problem is being exploited. It may be. It's not an easy attack to exploit. It's probabilistic. But a lot of folks are actually also exploiting other microarchitectural attacks. So I believe we need to prevent it. That's a very good question, though. Any other questions? Okay, I'll see you tomorrow. Enjoy the coffee break.